Hello, welcome to our electronics education program. I'm Vincent Chang. We're going to continue our lecture series around the subject of MOSFET and focus on the current voltage characteristics. Part 2, Derivation. Let me say a few words before we move on. This lecture is quite different from the previous lectures on the MOSFET, because I'm going to teach you how to derive the MOSFET current voltage characteristics. So it's not only related to the semiconductor devices, but also related to the semiconductor physics. So it's kind of intimidating for most of the beginners. But if you really want to understand, because you are going to use the equation, the triode and the saturation in the future many times. But if you just want to memorize the equation and apply and use it, and without knowing how the equation coming from, then you can probably skip this lecture. But if you want to know where the equation comes from and how, and in depth, and looking for the in-depth understanding of the semiconductor physics devices, then this is the lecture. N-channel enhancement, MOSFET, source gate drain, body, the current symbol on the right. Here's the current voltage characteristics, the relationship between ID and the VD. We understand this kind of qualitatively. Let's focus on the triode region. Let me go back. We have saturation. We have the saturation and the triode region, right? Because saturation is simple. But what about the triode region? It's a little bit complicated. So let's focus on the complicated part. This lecture only teach you about the IV characteristics in triode region. Let's focus on the triode region. Here's the triode region, the non-pinch-off region. The triode region means the non-pinch-off region. The source, non-pinch-off. The drain is non-pinch-off. 4 steps to derive the IV characteristic in the triode region. First, step 1, figure out the inversion charge per unit area. Number 2, find out the differential resistance along the channel. Number 3, apply differential Ohm's law. Number 4, try to integrate the whole channel. Charge, resistance, Ohm's law, and then integration. Again, this lecture only focus on the triode region. Channel length, L. Let's define the coordination. The y-coordinate. The y-coordinate. On the left-hand side is y equals 0. On the right-hand side, y equals L. L represents the channel length. So any point along the channel is a variable y. Any point along the channel, y. Let's try to find out the channel potential, the y, in reference to where? The ground. Ground is on the source side. So the voltage across between y, any point is a variable. Y and the source is what we call the channel potential, denoted by V of y. Now watch carefully. V parenthesis y. V of y. Now step number 1. Here comes the step 1. Find out the inversion charge. Surface inversion layer. The inversion charge Qn of y is the variable. Q equals what? If you learned physics before, the Q equals CV. What's C? What's C? The oxide capacitance, the gate-oxide capacitance. Permittivity of the oxide divided by the gate-oxide thickness, the gate-oxide capacitance. Q equals C times V. What V? The voltage across the MOS structure, right? The voltage across the MOS structure. But the voltage is a variable because the Y varies. So the voltage also varies. So now, what's the voltage of the question mark? Of the green question mark. Then you need the kickoff voltage law. Kickoff voltage law. So now, VGS, V of Y. So the answer, VGS minus V of Y. VGS minus V of Y. Q equals CV. But if this is the parallel plate capacitor, this is the answer. But it's not a parallel plate capacitor. You learn from physics. This is the MOS structure. So that's the major difference between the parallel plate capacitor and the MOS capacitor. The concept of threshold voltage. The concept of threshold voltage. Only when the applied voltage is greater than surpass what voltage? Threshold voltage, the charge can be induced. Can surface inversion layer can be formed. The channel can be formed only when the applied voltage surpass the threshold. Then, because the oxide capacitance is per unit area, so the dimension for this charge is also per unit area. So it's coulomb per unit area, coulomb per centimeter square. So now the first step is done. Are you okay? A little bit intimidated. Okay, let's move on to the second step. Differential channel length. Differential channel length. Let's move on from Y to Y plus a differential length dy. Because it's the concept of a differential, right? So within a very small distance, the channel behaves like a resistance. Differential resistance between Y and Y plus dy. The differential resistance dr between Y and Y plus dy. So how to calculate this? Now I want you to maybe try to find out the formulation for the dr. You can just think about in physics. So how to calculate a linear resistor? It's proportional to what? And inversely proportional to what? Proportional to length, right? And inversely proportional to what? Cross-sectional area. And the coefficient is what we call the resistivity. It's the resistivity. As I just mentioned, you can just put out, because this is kind of two-dimensionless, expand to a three-dimensional structure. From two-dimensional to three-dimensional. So see the three-dimensional differential resistance structure. This is the depth, the channel depth, and this is channel what? Channel width. So channel depth, the depth of the channel, the depth of the surface inversion layer, the depth, as I just mentioned, the resistance, the linear resistance is proportional to length, which is dy, and inversely proportional to the cross-sectional area. And the coefficient is what we call the resistivity, the resistivity. Now, for the cross-sectional area, it's the depth times width. Cross-sectional area, depth times width. What about the resistivity? Based on the semiconductor physics, it's 1 over electron concentration, electronic charge, and the electron mobility. 1 over NQ mu n, resistivity. And now, let's rearrange a little bit. Just pull out the W and the mu and put NQ depth together. So what is the NQ times depth? Electron concentration, electronic charge, and depth, which is exactly the same as the inversion charge per unit area. Inversion charge, you can check the dimension by yourself. NQ times depth, the channel depth equals the inversion charge. Now, we have completed the first 2 steps. Now let's move on to the step number 3, differential Ohm's law. And number 4, the integration part. Differential Ohm's law, because it's the linearity remains within a very small distance. The voltage across the dr between y and y plus dy is dV. And the current is ID. Differential Ohm's law tells us that dV equals ID times dr. The physical meaning of this equation is what? Any nonlinear IV curve, if you just cut a very small segment, can be treated as a straight line. Okay? And the concept, the meaning of the straight line is what? Correspond to a linear resistor. Ohm's law can be applied. It's valid only within a very small segment. Now let's just pour in, let's just plug in the dr, the formulation for the dr, dy divided by w mu times q. And now let's replace the Qn of y by the blue equation. Again, the channel potential, the voltage across the VGS minus V of y represent the voltage drop across the MOSFET structure at the point y. As I just said, let's replace the Qn of y with the blue equation. Now you can get the equation on the bottom. Right? So ID times dy equals, and they move to the left-hand side. All right? Mu C W VGS minus V of y minus Vt times, move to the left-hand side. So now, let's move on to the last step. Then integrating the whole channel. Because we just find out the relationship between current and voltage within a very small segment. To get the whole IV characteristic, we got to integrate the whole channel. On the left-hand side is position, is the length, y. On the right-hand side is voltage. For the position, for the length, integration of the whole channel tells us from the left end, the lower bound, to the upper bound, the right hand. The right end. The left end, y equals 0 to y equals L. So on the left-hand side versus the position. On the right-hand side corresponds to the voltage. So on the left-hand side, the channel potential, V, represents the channel potential. On the left-hand side, the lower bound is 0. What about the upper bound? On the right-hand side? What's the channel potential when y equals L? V, D, S. A little bit smaller, okay? You got to just zoom in there. VDS, the upper bound is VDS. So the left hand side is 0 to L, on the right hand side is 0 to VDS. If you learned the calculus before, this is quite easy. The left hand side ID times L. On the right hand side, because dV, so VGS minus VT, VT can be treated as a constant. Okay, so VDS minus VT times VDS. Minus V is a variable, so V squared divided by 2. All right? V squared divided by 2, and plug in the upper bound, VDS squared divided by 2. So pull out the 2, then here's the answer. Half mobility oxide capacitance, channel width divided by channel length, because L move from the left hand side to the right hand side. And to VGS minus VT, VDS minus VDS squared. For the trial region, again, this equation only applies in trial region. Here's the equation. Here's the equation to describe the family of curve, the relationship between ID and what? VGS and the VDS. ID and the VDS and the VGS. ID is controlled by 2 voltage variables. Remember? VGS and the VDS. This is it. This is it. This is the equation to describe the current voltage characteristics when the MOSFET is operated in the trial region. So now, sum up, 4 steps of derivation. Inversion charge, differential resistance, differential Ohm's law, integration. Step 1, inversion charge per unit area. Similar to what you learn from physics, Q equals CV. But you have to include the concept of threshold voltage. Step 2, differential resistance. Differential resistance. Number 3, differential Ohm's law. The linearity remains when the nonlinearity curve only deal with a very small segment. Number 4. Step number 4, integrating the whole channel. The left hand side from 0 to L, the right hand side from 0 to VDS. Here's the takeaway. Once you understand where this equation coming from, then we can just apply this in the future when we try to analyze the device, the MOSFET, when it's in the trial region. So we have come to the end of this lecture. I hope you learned something from this lecture video. Thanks for watching.